Our team, NPK4EVER, dealt with the challenge of manure management from large animal farming operations as a new resource for fertilizer and carbon offsets. I'm James Hunt and provided mentorship for the team alongside Jordan Fazy of Finite, Tasman Hussein, Mahmoud Shahara, Kelly Ziering, and Danny Jones of North Carolina State University, and two students from North Carolina State University, John Hinnick and Silas Huckins. Large animal protein manufacturing facilities create an excess of nitrogen, phosphorus, and potassium, which ends up overwhelming the local landscape where this animal protein is being produced. Simply, there's too much fertility for healthy ecosystems to endure, in particular with regards to waterways. This waste is stored and often land applied on sites near the animal protein manufacture facilities.
Estimated that in the US alone, almost $3 billion worth of manure-based fertilizer gets wasted every year. The challenge in the past has been that there hasn't been available technology in order to recycle animal waste cost efficiently. Animal waste is very wet, and drying is a very energy intensive process, and that's what's needed to be done to make manure-based products transportable.
The benefit of drying this material out is that it's a huge way to offset carbon both on these animal farms and in the fields where the new fertilizer could be applied. And that's what NPK4EVER is all about. Fertilizer going in a circle, forever. Today, most nitrogen fertilizers produced at energy-intensive factories that consume 1% of global energy supply or mined from rock deposits. Simultaneously, demands for protein have created abundances of animal manure leftovers from the same corn and soy cultivation, which uses these chemical fertilizers to grow feed for chickens, pigs, and to a lesser extent dairy cattle. These concentrated producers have too much nitrogen, phosphorus, and potassium from their residual waste streams. In 2017 alone, more than 61 million metric tons of emissions came directly from manure management, as well as a more meaningful 227 million metric tons from agricultural soil management and 38 million metric tons from using synthetic nitrogen on cropland across the country. Farmers are being incentivized to offset carbon, and we are in a period of price discovery led by many large agricultural firms where paying farmers for verifiable carbon offsets through using nutrient cycling to build healthy, diverse, and biologically rich soil means that we need a new approach to fertilizer, one that leverages naturally derived manure as an alternative to emission-heavy synthetic nitrogen. Some companies are even paying up to $20 per ton CO2 offset on farms around the country.
So one of the ways that soil carbon is built is this cycle of animal manure and then plants taking it up and all of the microbes sort of digesting those different inputs, and that's how soil is built. It sounds like by taking where there's these excess waste sources, transforming it so that it can be applied on traditional agricultural systems outside of the zones where there's already too much nutrient in the soil, that can advance what some people are calling regenerative farming, in your opinion.
Yes, that's absolutely right. So just as you say, regenerative farming is all about grazing animals on land, using their hoofs to incorporate the carbon that's based in their manure and the nutrients back into the soil as they're grazing over the land. A lot of land in the US isn't suitable to that, particularly because there just aren't enough animals to graze all of the Midwest, for example. And so our product creates a carbon source to essentially replace the regenerative system with these inputs that can provide soil fertility without the complexity of rotationally grazing the fields.
Okay, so what do I have to do?
We worked with Danny Jones and Tasman Hussein's code, originally intended to examine ethanol sourcing and factory locations, and we modified it here so that it could accommodate the manure feedstocks as opposed to ethanol.
Where we actually used our data for the model We defined a few characteristics here to make sure we had the right nutrient makeups, factors for how much it costs to travel and such right here. Here is our target price for the end result. And that's per carbon ton, I believe.
Yes.
And then here is our actual model. And this is where the bulk of the code was within SAS.
We used USDA data to query the nationwide distribution of this concentrated manure, and to start to map out the relationship between raw material sources, drying facilities that served as preprocessors, and helped reduce the cost of trucking where the manure was wet, and the primary constraint of this difficulty in transportation was effectively trapping the nutrients in watersheds and causing eutrophication issues, among others. Limiting the counties to those with major confined animal feeding operations across poultry, chicken, hog, and dairy facilities, we identified 1,060 counties which accounted for between 112 and 334 million metric tons of emissions per year.
Okay, I see what you're saying. Okay.
We used R and SAS to integrate county-level data across the country for different kinds of livestock, including poultry, swine, and dairy facilities. We then identified potential depots where the manure from these confined animal feeding operations could be consolidated and dried before being shipped more cost-effectively to fertilizer factories around the country. To move the manure between these facilities, we had to identify coefficients for fixed and variable cost and tune in our model even tighter.
Okay, let me draw what I think it's better if I draw.
Yeah.
The easiest way is just to multiply row 1, 2, and 3.
Using the SAS operations research capabilities, we were able to ask how much carbon offset would be possible at different levels of pricing for carbon per ton.
Why don't we just multiply it in the grower payment inside the code?
Our model showed us the price curve for carbon offsets that would stimulate a new fertilizer economy on small farms around the United States. At $105 per metric ton, we started to find solutions where a new circular fertilizer economy could work. Our model's outputs dictated which counties would be eligible to cost-effectively ship raw manure to depots for pre-processing and on to fertilizer factories for processing. On the x-axis is the price per metric ton of carbon, and on the y-axis is the total number of depots or factories that could be constructed at that carbon offset pricing level. The black dots represent available manure sources, and the blue dots represent depots for processing the raw manure. Here you can see as the price increases, so too do the depots, where here the factories that receive from those depots at the low price level and the high price level manifest. The fertilizer, though, doesn't end its journey at the factory. Naturally, it could go on to be land applied in fields, an opportunity for further analysis on our part. A company, Anuvia, that currently uses such a biosolids-derived fertilizer product claims that it reduces greenhouse gases on each acre planted by 32%, in addition to the gains that we've already described by offsetting the raw emissions from the manure itself. We've taken steps to identify a solution for a problematic waste stream arising from animal protein manufacturing, and further work would reinforce and help further incorporate associated carbon impacts to better understand the cumulative results from using recycled manure in a circular economy that focuses on improved nutrition and reduced carbon emissions.